Hello, and welcome to our 300th video. This video is going to be about dichlorocarbene and some of its important reactions. Curiously, the number 3 being the number of the counting, will actually play a significant role in this video. Let us first begin with the compound trichloromethane, which has the more common trivial name of chloroform. We can see that it is a haloalkane, and we know that haloalkanes have very low acidity. If it were to act as an acid, it would lose H plus and be left with a conjugate base that was an anion. Now we know one way to stabilize anions is the presence of electron withdrawing groups, and we know that chlorine is one of the most electronegative elements, so it is going to be a powerful electron withdrawing group. Here we have 3 of these powerfully electron withdrawing groups, which therefore leads to the fact that chloroform is more acidic than a typical alkane would be. Now, let's react chloroform with a very strong base. Typical very strong bases would be sodium hydroxide, potassium hydroxide, and potassium tertiary butoxide. These are sufficiently strong bases to deprotonate chloroform. We have this bond breaks, and we're left with the following ion. The trichloromethanide ion. This is the conjugate base of chloroform acting as an acid. However, this particular species is unstable and it immediately loses chloride ion. Bond so that the electrons leave with chlorine as chloride, and we're left with the following species, which we call dichlorocarbene. Notice, first of all, that surrounding carbon, we have 1, 2, 3, 4, 5, 6. We only have 6 electrons. So we realize that carbon likes to obey the octet rule. If it has only 6 electrons, it's going to be quite electron deficient. And when we have these 6 electron carbon species where carbon is neutral, we call these carbenes. This particular one has 2 chloro substitutions, so we call it dichlorocarbene. Notice that we've drawn the 2 non-bonding electrons on carbon as a lone pair, as if they are in the same orbital. And this is one of the possibilities. So around carbon, if we have this particular configuration, there's also an empty orbital over here. So we can think of this particular situation as having 2 electrons that are paired in one orbital, and we have another orbital that is completely empty. When we have this situation, we have a certain amount of terminology. We recognize that the 2 possible m sub s spin states for electrons are plus a half for an up electron and minus a half for a negative electron. So we can add together, so that's m sub s. We have one that's plus a half and one that is minus a half. So we can also construct a total spin, which is this s, in which case we add together the values of m sub s for the 2 electrons. So we have a plus a half and minus a half. That gives us a total spin of 0. So whenever we have paired spins, we have an overall spin, capital S, of 0. Related to the total spin s, we have a quantity which we call this multiplicity, the spin multiplicity. And the formula for this spin multiplicity is, by definition, 2s plus 1. So in the case where we have two electrons in the same orbital as a lone pair on carbon, the multiplicity 2s plus 1 is going to be 2 times 0 plus 1. So this gives us a spin multiplicity of 1. We refer to this as a singlet. So this is singlet carbene. On the other hand, it is possible to form dichlorocarbene in such a way that we have the two electrons not together as in two different orbitals. And we can represent that particular state by having an up electron in the first orbital and an up electron in the second orbital. So in this case, the m sub s values of the electrons, because they're both up spins, are plus 1/2 and plus 1/2. So this gives us a total spin, capital S. We add up the m sub s values, and this gives us a total spin, 1/2 plus 1/2 is equal to plus 1. So in one situation where both electrons are in the same orbital, the total spin S is equal to 0. When they are in different orbitals, the total spin S is equal to plus 1. So what is the multiplicity in this case? Well, recall that by definition, the multiplicity is 2s plus 1. We know that in this case, s is equal to 1. 2 times 1 plus 1 is equal to 3. So the spin multiplicity of this version of carbene is 3, and we refer to any species that has a multiplicity of 3 as a triplet. So we see that there's two different versions of dichlorocarbene, depending upon whether the electrons are in the same orbital or different orbitals. That affects the total spin, and it affects the total spin multiplicity. So we refer to the blue case here as singlet carbene, and we refer to the case down here, which we've done in purple, as triplet carbene. Please see the following diagrams to see computed structures for singlet carbene and singlet dichlorocarbene and triplet dichlorocarbene. For the remainder of this video, we are going to restrict our attention to the reactions of singlet dichlorocarbene. The particular reaction we are going to emphasize is the reaction where dichlorocarbene inserts into the double bond of an alkene and ultimately forms a cyclopropane derivative. One of the things that's important about this reaction is that if we start with singlet dichlorocarbene, the reaction is concerted. It takes place in one step. Secondly, it always occurs with a cis addition. So we have retention of the stereochemistry at the alkene. Show our electron flows here. The result is a cyclopropane derivative. So these two carbons come from the ethylene that we started with. The third carbon of the ring comes from the dichlorocarbene. As we'd expect, the three-membered cyclopropane ring is planar, but then the chlorine atoms are either above and the other one is below the plane of the cyclopropane ring. In this particular case, we don't see anything special as far as the stereochemistry because we're starting with ethylene. We'll see that when we have more highly substituted alkenes, that we end up having retention of configuration in the cyclopropane derivative. In this case, we have 1,1-dichlorocyclopropane. Please see the following slides to show the computed structures of the transition state for this addition and for the final product. Suppose, instead, that we react our dichlorocarbene with a different alkene, in this case, propylene, or in IUPAC terminology, propene. We know that dichlorocarbene will add to the alkene double bond in such a way as to make a cyclopropane derivative. So let's see what that is going to look like in this case. So again, 2 of the 3 carbons of the cyclopropane ring come from the 2 carbons that are attached in the alkene. The third comes from dichlorocarbene. And we know that attached to this 1 carbon, we're going to have 2 chlorine atoms, one above the plane of the ring and the next below the plane of the ring. We also now have a 3rd carbon that was attached to the alkene. So this will now be above the ring. Now, in this particular case, whether it adds above or it is above or below the ring is not significant. It's not chiral because the structure that we have here, that if we rotate it and flip, we could have the methyl group be below the ring just as well. So, but here we have propylene and the addition, and we end up getting a 1,1-dichloro 2-methyl cyclopropane. Please see the following slides to see the computed structures for the transition state of this insertion and for the final product that we have here. Now, let us react our dichlorocarbene with a different alkene. In this case, we have the cis isomer, 2 methyl groups are on the same side of the double bond, of 2-butene. So this is cis-2-butene, and this is a case where we'll actually be able to see the stereochemical implications of the fact that the reaction of singlet dichlorocarbene is stereospecific. Again, we can always start by putting down 2 of the carbons of the 3-membered ring as coming from the alkene. The 3rd carbon comes from dichlorocarbene. And we know that relative to this 3-membered ring, that one of the chlorine atoms is going to be above the plane and one is going to be below the plane. But now what about the 2 methyl groups? So since these are each on the same side, we have to put them at relative to the ring. This one is going to be above the ring. And since the cis are on the same side of the double bond, this one also has to be above the ring also. The key is whenever you have cis substituents, they are going to be cis once we make the 3-membered cyclopropane ring. We could just as well have drawn these with both these below the plane. The important thing is that since they're on the same side of the double bond here, they have to be on the same side of the plane generated by the 3-membered cyclopropane ring. So here we have cis 1,1-dichloro 2,3-dimethyl cyclopropane. To better appreciate the effect that the addition of singlet dichlorocarbene has when it adds to alkenes, as far as a stereochemical sense, a nice example is now to look at trans-2-butene. So here, the two methyl substituents at the end are on opposite sides of the double bond, which makes them trans. So let's see how that affects our final product. We can start out with the first two carbons from the alkene. The third member of the cyclopropane ring comes from dichlorocarbene. The two chlorine atoms are both attached to the same carbon, and they come from dichlorocarbene. So we can see the dichlorocarbene pieces still together there. But now what happens as far as the methyl substituents? Well, since they are trans, they have to be on opposite sides of the plane of the ring of cyclopropane. So we realize that these three carbons are all in the same plane. One of the methyl substituents is going to be above the plane of the ring, whereas the second one has to be below the plane. So one is above and one is below, because they're trans in the original alkene. So what is it? This gives us trans 1,1-dichloro-2,3-dimethyl cyclopropane. Let's try a slightly different alkene in this case. Here we're going to use 1-butene instead of 2-butene. Let's see how that affects the final product. So again, the two carbons that are attached in the alkene double bond form 2 to 3 members of the 3-membered ring. The third carbon comes from dichlorocarbene. We need to put in the two chlorine atoms. So we'll put one as being above the plane and one being below the plane, because that's how it will be. So now notice that attached to the first carbon of the alkene, all we have is hydrogen as a substituent. So this stays as hydrogen. On the other hand, the second carbon has an ethyl group rather than a methyl group attached. So that tells us that either pointing up or pointing down, it won't make a difference in this case, we're going to have an ethyl group. So we have CH2, CH3. So this is a nice example because it shows us that depending upon how we substitute our alkene, we can have more substantial substitution than merely methyl groups or hydrogens. So if you have an ethyl group, this whole group will either be above or below the plane. So please take a look at the following figures that show computed transition states and the computed ground state structure of our product, which in this case is going to be 1,1-dichloro-2-ethyl cyclopropane. For our final example, we're going to use cyclohexene as our alkene. Even though this looks more complicated, we can apply the same principles that we've used already to determine what the final structure is going to be. So remember, as always, we take the two carbons of the alkene and they form 2/3 of the cyclopropane ring. The third member of the ring comes from dichlorocarbene. We recall that cyclopropane rings are highly strained, but they're planar. So this chlorine will be above the plane, one will be below the plane. And then we have the remaining 4 hydrocarbons. So, continuing. Now, it's important to realize that, again, because these are cis to each other, these sides, they have to either be above or below the plane relative to the cyclopropane ring. So, let's draw them carefully here as both being above the plane. Put the carbon there. I'll also draw the carbon explicitly. And then show that they're both above the plane in this particular case. A little neater here. So again, this is a consequence of the fact that reaction with singlet dichlorocarbene is a concerted reaction that is cis, so it preserves the stereochemistry of the original alkene. I thank you very much for your attention. Have a good one, and please like or subscribe.